All right, so welcome everyone to the Schubert seminar. Today we're happy to have Giordano Cotti from Lisbon telling us about enumerative geometry of partial flag varieties and prime numbers. Please take it away, Giordano.
So, first of all, I would like to thank you very much for this invitation. I'm very happy to be here tonight for this night with you, even if online. And what I plan to do in the next, say, in the next hour, is to discuss about some connection I recently studied between enumerative geometry of partial flag varieties. More precisely, as you will see, I will focus on Gromov Witten theory, quantum cohomology, and prime numbers. As Leonardo said, it's quite rare to find these two topics apparently so far from each other in the same slide. All right, so I want to start with, by sending you immediately one of the main leitmotif of this talk. I mean, the main message I would like to send you is that, as crazy as it may seem, there is a connection between enumerative geometry of homogeneous spaces. Today I will focus on partial flag varieties and prime number theory. More precisely, such an interplay will be revealed by studying the generacies of so-called quantum spectra. So here you are a very basic plan of the talk. In the first part of the talk, I will I will recall you basic elements in Gromov Witten theory, and I will introduce some object called quantum spectra. After that, I will discuss a Coalescence phenomenon in the case of Grassmannians, and I will also recall the so-called quantum Satake principle that I will use, I used to study this Coalescence phenomenon. After that, I will introduce some sort of limits of these quantum spectra that I will call semi-classical limits of these spectra in the case of partial flag varieties. And at that point, I will let appear this connection with prime numbers. In the last part of the talk, I will focus on the study of three double sequences, three arithmetic double sequences that will play, as you will see, some special role to creating such a bridge. All right, so let me start with a very rough and basic introduction to what quantum cohomology is. So, all right, here I will denote by X a smooth projective variety over the complex numbers. I will denote by h of x the even part of a classical cohomology with complex coefficient. I will also denote by eta the Poincare pairing defined at the level of cohomology classes by taking the couple product of two classes and then integrating over the variety X. Well, for sure, I can interpret such h of x as a finite dimensional complex vector space equipped with such a Poincare metric, which is, I can interpret it as it is a symmetric, non-degenerate bilinear form. And I can also interpret it as a pseudometric, on this linear manifold. A pseudometric which is manifestly flat because we have just a metric on a complex vector space, and I can attach to it a Levi-Civita connection, a flat Levi-Civita connection. Well, the fact is the following. Gromov Witten theory allows us to associate with X a family of deformations of a classical cohomological algebra of X. Such a family is the quantum cohomology. the picture one should have in mind is the following. Such a deformation of a classical product is performed by taking into account some information concerning curve countings on this variety X. And the idea is the following. You collect all this information, you pack all this information into a generating function. Of course, one can deal with such a generating function from a formal point of view, but actually today I will just focus on cases in which such a generating function, the so-called Gromov Witten potential, is actually convergent. And I will denote by M the domain of convergence of this Gromov Witten potential. Well, it turns out that I have, okay, such an M then is a domain, a complex domain in some Cn, in some space Cn. And it turns out the following, that each holomorphic tangent space at points of this domain are equipped with a Frobenius algebra structure. Let me recall you that Frobenius algebra structure is a commutative, associative, unital algebra whose product is actually compatible with a non-degenerate bilinear symmetric form that in this case can be exactly identified with the Poincare metric. Indeed, such a domain M should be thought as an open domain inside the H of X I introduced before. All right, when I say compatibility condition with a metric, I mean that any operator of multiplication by a vector field is self-adjoint with respect to such a bilinear pairing. Well, I have to define, okay, so I claim that we have a family of algebras in each tangent space, holomorphically depending on the point. And I also have to explain how such a product is defined. Well, the product is defined implicitly by the formula you find here at the very bottom part of the slide. So we define the product, the quantum product of two classes, two tangent vectors in one point, V1 and V2, by taking the pairing with the Poincare metric with any arbitrary element V3. And we define it, we require that such a pairing equals the third covariant derivative of f of a Gromov Witten potential, this generating function I was speaking about. More precisely, the Gromov Witten potential as follows. What you have to keep in mind is the following moral definition of Gromov Witten invariant. All right, so what Gromov Witten invariants want to do is to count curves on X. So you interpret X, if you want, as a target space, and then you consider all possible maps from a genus G Riemann surface with a fixed topological degree, beta, in this slide. And the fact is that actually what we want to count are curves with some prescribed incidence conditions. So how to formalize that? Well, we first fix some subvarieties V1, V2, Vk in X. And we also consider Riemann surfaces with marked points, in particular K marked points, P1, P2, Pk. And then we just consider the maps mapping the ith marked points into the ith fixed subvariety of X. All right, so we have constraints on the degrees of a map. We have constraints on the images of these marked points, but we should never forget that what we actually want to do is to count true curves on X and not parametrized curves. So what we should do is to define the Gromov Witten invariant morally as the number of such a maps modulo automorphisms of a surface surface with marked points. All right, so this is the moral definition of a Gromov Witten invariant of genus G, k marked points, and degree beta. In this talk, in quantum cohomology, we just consider the genus zero sector. So we just consider rational curves on X. And indeed, the Gromov Witten potential, this function that you see in the top of the slide, is just a collection, is an exponential generating function for all Gromov Witten invariants of genus zero with arbitrary number of punctures and arbitrary degrees. All right. For us, for today, it will be a crucial ingredient, also a distinguished vector field on the domain M of the slide, of the previous slide. The domain M is the quantum cohomology of X, and the structure that I described with hands in the slide before is a Frobenius manifold structure. Well, on Frobenius manifold structure, you always have a distinguished vector field, the so-called Euler vector field. Euler vector field is an object, is a holomorphic vector field on the Frobenius manifold, which encode information about the homogeneity of the generating function we are considering. And indeed, such a vector field satisfies the following remarkable identity. If you take the derivative of a generating function with respect to such a vector field, what you obtain is a scalar multiple of the same function. The scalar is 3 minus the complex dimension of a variety X you consider, plus at most quadratic terms in coordinates, in dual coordinates with respect, dual coordinates in some basis. Well, you fix an arbitrary basis of the vector space H of X, the ambient space in which M, the Frobenius manifold, live. All right. Actually, in this talk, I will just consider not the big quantum cohomology, that is the whole Frobenius manifold, but I will just focus on the small quantum locus. That is to say, the family of Frobenius algebras attached to points along the H2, the group H2, the second cohomology group. Well, putting everything together along such a points, we have a restricted small quantum product, which has explicit expression as follows. So V1 times V2, and the product will be labeled by a point of the small quantum locus, equals such an explicit expression. So we have a series in this parameter Q. This parameter Q is just a point in a complex torus whose dimension equals the Hodge number 1, 1 of X. And the coefficient of this Q beta equals is implicitly defined via this equality. We require that the class bracket V1, V2 beta, if you take the pairing, the Poincare pairing with an arbitrary class V3, it has to equals the Gromov Witten invariant V1, V2, V3, genus 0, 3 mark points, and degree beta. All right, if we go back in the previous slide, as you can see, this Euler vector field, so this vector field encoding information about homogeneity property of Gromov Witten potential, if restricted to the small locus, it just coincides with the first-chain class of X. The Euler product is just a perturbation of the first-chain class, and it equals the first-chain class along points of the small quantum cohomology. All right. So, what is the quantum spectrum of X at the point Q? It is just the spectrum in the sense as a multiset, that is, I will keep track of elements with multiplicities, is the spectrum of the operator of quantum multiplication, small quantum multiplication by the first chain class of X. All right. There are many reasons of interest for studying this quantum spectrum. Well, first of all, here I just mention 5 of them. First of all, the quantum spectrum is an object which is a main character as long as you want to develop the isomonodromic approach to quantum cohomology. Frobenius manifolds, at the core, at the analytic core of Frobenius manifolds, there is indeed the isomonodromy theory of differential operators on complex domains, linear differential operators on the complex domain with rational coefficients. And it turns out that what you can do is actually to associate with X a family of such a linear differential operators. Such a family is called the quantum differential equation of X. It turns out that such a differential equation, the quantum differential equation, typically always admits two singularities. A Fuchsian singularity at the origin of an abstract auxiliary complex line, and a singularity of Poincaré rank 1 at the infinity of this auxiliary complex line. Well, it turns out that the quantum spectrum rules the asymptotic properties of solutions of these quantum differential equations and also the Stokes phenomenon of these solutions. That is, strictly speaking, are discontinuous change of the asymptotic expansion, the Poincaré asymptotic expansion of solutions at infinity of this quantum differential equation. A second main motivation for interest in studying quantum spectrum comes from the work of Galkin, Golisov, and Diritani concerning the conjecture O. Conjecture O essentially is a conjecture prescribing, giving some qualitative description of quantum spectrum for Fano varieties. But also, let me mention other interests coming from interactions with an apparently different aspect of a geometry of X. Up to now, I am speaking about quantum cohomology, which something which is actually on the symplectic side of a geometry of X. But it turns out that, conjecturally, but seen in many examples, it turns out that actually there is a connection with the complex geometry of X. And in particular, there is a connection between Stokes phenomenon of quantum differential equations of X and semi-orthogonal decompositions or exceptional collections in the derived category of coherent sheaves of X, seen as a complex variety, as a complex manifold. And in such a context, I mentioned just the two big conjectures. One is Dubrovin conjecture, claiming exactly, well, the statement of Dubrovin conjecture can be very briefly described as follows. There is a qualitative part prescribing the equivalence of a semi-simplicity condition of quantum cohomology with the existence condition of full exceptional collection in the derived categories of coherent sheaves. And there is also a more interesting part, a so-called quantitative part, which wants to prescribe the values of some numerical invariants attached to the quantum cohomology, starting from the exceptional objects of these collections. But there is also another interesting conjecture, the Kuznetsov-Smirnov conjecture, which somehow claim the following, that the degeneracies of a quantum spectrum are reflected on orthogonality conditions in the exceptional collections arising in this context. A further point of interest is a conjecture due to Maxim and Koncevich on the structure of quantum spectra of low-ups, and related also to that, let me also mention a very new exciting research areas due to Kazarkov, Kontsevich, Pantev, and Yu, in which essentially they were able to construct new birational invariants known as atoms or chemical formulas from quantum cohomology, from quantum products. This construction of these atoms and chemical formulas essentially are very refined version in a p-adic context of this quantum spectrum I defined before. As an example, take X projective space Pn. The small quantum cohomology admit this presentation that you can read here. So it's, as you can see, the deformation of a classical cohomology algebra in which you have one deformation parameter Q. And First-rank class equals n+1, the hyperplane class. And it turns out that the quantum spectrum is essentially, well, is a rescaling of the set of a n+1 roots of unity. Another example, the case of Grassmannian, the simplest example, G24. In G24, in the Schubert basis, you can prove that the small quantum product by the Fernstein class of X admits such a matrix representation. And if you compute the spectrum of this matrix, what you can discover is that now you have a spectrum which is not anymore simple. You have some eigenvalues with higher multiplicity. In particular, you have 4 simple eigenvalues and a double eigenvalue. All right. All right. When I started during my PhD to study, well, my point of view came from the Brovin conjecture. So what I had to study were quantum differential equations attached, in my case, to Grassmannians. And you see, from the point of view of differential equation, coalescences of eigenvalues, as you can see here for G24, represent a very delicate problem from the analytical point of view. Because in that case, you don't have anymore the well-established theory of isomonodromy deformation. If you go back even to the works of Poincaré, Schlesinger, Fuchs, Painlevé, nobody ever addressed the study of isomonodromy deformations in presence of these coalescences of eigenvalues. So a first thing I had to do was to understand when this coalescing phenomenon, that is a phenomenon of eigenvalues with higher multiplicity, appears and when not. You see, what I thought was, I had a very human expectation. I told myself, oh, come on, what I want to study is a resonance phenomenon. Resonance phenomena are rare phenomena somehow. So I would have expected that if I consider the class of all Grassmannians, such a coalescence phenomenon should have been a rare phenomenon. And well, what I discovered experimentally at the beginning was exactly the opposite. So imagine to represent the class of all Grassmannians in a Tartaglia-Pascal triangle. So you replace the binomial coefficient n choose k with a Grassmannian GKN. And you color in red those Grassmannian which do not manifest coalescences of eigenvalues, and in green you represent Grassmannians which do represent, which do manifest, which do have coalescences of eigenvalues. Well, when I asked my computer to draw such a picture, I was shocked by the density of green dots. It turned out apparently that this phenomenon, this coalescence phenomenon, was much more appearing than what I expected. And not only, I actually realized that there were some red lines, lines with just red dots. And then I started to count these red dots, and I realized that these lines correspond to Grassmannians of subspaces in Cn where n is a prime number. Indeed, here you have the following result, the following theorem. The Grassmannian GKN, that is the Grassmannian parametrizing k-dimensional subspaces in Cn, manifest a coalescence of eigenvalues of the quantum spectrum if and only if k is between the smallest prime number which divides n and n minus such a smallest prime divisor of n. How to prove such a result? So how did I prove such a result? The key fact I used is the following. The quantum spectrum of a Grassmannian GKN can actually be reconstructed from the much simpler quantum spectrum of a projective space Pn-1. In the previous slide, recall that the spectrum of projective spaces is simple. You never have coalescences, and it represents the one of the two red border of this triangle. The other border is represented by projective spaces, dual projective spaces of hyperplanes. The fact is that we have a classical, already at the level of classical cohomology, we have the so-called classical Satak identification, which consists into an isomorphism of classical cohomology of Grassmannians on one side, and on the other side, we have an exterior power, the kth exterior power, if we consider GKN, of the classical cohomology of Pn-1. And there are many ways to see this, to say at the classical level. One way is to invoke the Ginzburg geometrical Satake correspondence for affine Grassmannians. There are also results, I mean, the same statement actually has been proven in a more, so to say, in a more simple way by Ellingsgrud, Ströme, and in the symplectic context by Martins, a student of Donaldson. But let me also mention that the same result can actually be established by using Veleterio-Gatto's theory of Hasse-Schmidt derivations, a very beautiful theory which allows you to prove a statement like this in a uniform way for all Grassmannians GKN with fixed n and varying k altogether. The remarkable fact is that such a classical result admit also a quantum extension. And again, each of the three classical approaches, of these three classical ways to establish this result, admit a quantum extension. For example, the Ginzburg work on perverse sheaves on loop groups has been generalized in some cases by Golishoff and Laurent Manivelle. It is the so-called quantum Satake principle. But also let me mention that results of Bertrand, Chocan-Fontanin, Kim, and Sabat extend in the quantum context results of Ellis-Groth, Ströme, and Martins. And remarkably enough, the theory of Gatto actually is already so powerful that actually it already encodes the quantum case. So the quantum, and even quantum equivariant case can be established again by using Hasselschmitt derivations. All right. So what I wanted to do then is the following question. I wanted to understand such a phenomenon that I noticed for Grassmannians. Is there any hope to see something like that for more general partial varieties? All right, let me fix some notation. I will first introduce a multiplet lambda, lambda 1, lambda capital N, a multiplet of positive integers whose sum is equals n, and I will denote by f lambda the partial varieties parametrizing chain of subspaces in Cn whose uh, consecutive quotients have dimension lambda I. Well, the fact is that for varieties as such, in which capital N is bigger than 2, strictly bigger than 2, what happens is that the small quantum cohomology depends not anymore on a single parameter, but it depends on many parameters, many small quantum parameters. And if you study the dependence of a quantum spectrum, of a small quantum spectrum on these parameters, well, it turns out that depending on the choice of these quantum parameters, this quantum spectrum may be simple or not. So in other words, you will have inside this parameter space, you will have some subvariety, some sublocus, along which you have coalescences of eigenvalues, so a richer structure of the spectrum, and generically you don't have these coalescences. So the first problem for me was to understand what is the question I may pose. And well, the idea I had was the following: to take what I call a partially classical limit. That is, of all these quantum parameters, let me just froze to zero all but one, and let's see what happens. All right, so let me just define what I mean by semi-classical spectrum to formulate two questions, and then I will do a small pause. So for each I from 1 to capital N minus 1, I recall you that capital N gives you the length of a chain of subspaces you want to parameterize. And for each such a parameter I, we will have a parameter Qj, a quantum parameter Qj. So what I do is the following: I fix such an I, and I set all the quantum parameters not corresponding to such an I equals to 0. And in this way, what I obtain is not anymore a single spectrum, but I have n minus 1 possibilities, possible different spectra that I call semi-classical spectra. And all of them are depending now on a single parameter Q. Two questions. I want to pose two questions. First question: is there any hope for a Gromov Witten theoretical meaning of this limit procedure or not? Second question: is there any phenomenon similar to the coalescence of Grassmannians for this spectra? Well, now we will do a stop. Spoiler, as you can see from the theorem, the answer will be yes, at least for the second question.
All right, so yeah, thank you very much. Let's take maybe a 3-minute break, so until 5:09 local time here.